What's happening, guys? Let's get going. We got this test number 2 quiz review video. Let's do it. So, first one, 35th percentile of a population is the number X, such that definition of percentile, we're always going less than or equal to that value. So we're going for less than or equal to, and that's kind of your definition. You're less than or equal to for the percentage of the population. We'll have a more exact example actually in the very next question. But the 35th percentile, less than or equal to, just to visualize it, if it was a normal distribution, not all distributions are normal. But if it was a normal distribution, and we're looking at 35th percentile, remember that this is going to be the 50th percentile because it's dividing exactly half and half. So we would call this number the 50th percentile for a normal distribution that also happens to be exactly equal to the mean, the mu. Depending on the situation, could be a mu, could be an x bar. This is going to be the 35th percentile. So the 35th percentile is going to be, I don't know, just ballpark it precisely where it is. It's going to be a smidgen more than that inflection point. This will be our 35th percentile there. So that's what we're looking at in this population. Let's look at that. So A, 35% of the populations are above. Actually, for the 35th percentile, 65% are above. And I believe that's actually letter B, and that's our correct answer. So there we go. We got our correct answer. 35% scores equal. That is absolute nonsense. Medians and means got nothing to do with that at all, unless it happens to be exactly the 50th percentile. By the way, the 50th percentile for normal distribution is the mu or the x, but by definition, the definition of the median's definition is the 50th percentile. That is literally what the median is. The most middle value is the 50th percentile by definition. All right, hopefully we're done talking there. Let's move on to the next question. All right, here are the exam scores for these 14 students in Miss Novak's statistics class. For these 14 students, I always recommend if they give you a total number in the class, you kind of circle it. It's going to be useful in this question, actually, because here is our number 85 right there. So our denominator is going to be 14 because we're trying to figure out what percentile is this person at, and it's at to less than or equal to, right? So it's less than or equal to that point. So how many are this one? And then we have to add up all of these. It's going to be a little bit faster. Instead of counting up all of these, count the ones that aren't. There are 3 that are not, and therefore if we add up all of these, we will get 11 over 14. Don't forget to multiply by 100 to get that percentage in the end. So I'm just going to go ahead and do my little calculator. I always recommend for students just to use the alpha y equals so you don't end up messing up that stuff later. And if you miss that, I apologize. It's the alpha y equals, and then the enter button at the bottom right hand corner is going to give us the fraction bar. Anyways, 11 over 14 times 100. We do want the percentage form, so this answer the calculator gives you of 550 over 7 is not too useful, but we can convert it back by again hitting alpha y equals, but this time we're going to use the number 4, the fraction to decimal, and vice versa button, and that's what we're expecting as our answer, 78.57%. It appears to be letter D here, 78.6%. All right, moving on to that question number 3. Consider the following cumulative relative frequency graph of these children who played the game skee ball at a birthday party. So, skee ball is fun. I'm a fan, not that great at it, but definitely a fan. What are the approximate values of median interquartile range? So we already talked about how the median by definition is the 50th percentile. Interquartile range by definition is Q3 minus Q1. This is the 75th percentile, and this is the 25th percentile. So we need to find the 50th percentile, 25th, and 75th. I don't know why I wrote 25th twice. This should have been a 2, and this should have been a 7. Okay, so Q1 is 25th, Q3 70. Anyways, so 50th percentile. So we need to go find where is 50. 50 is going to be about right there. And we just need to do our best to draw a perfectly horizontal line. If I had a ruler, I would actually get it. But it looks to be exactly a 70 is going to be our median. So we can already cross off letters A and B and C because those guys are not at the median. Again, this is our 50th right here. And then we're looking for 75th and 25th. So 75th and 25th, I would say that the 20, maybe a little bit above it, like right there, That appears to be our 25th percentile. Remember that 30th would be smack dab in the middle, so maybe halfway between, but right there is good. So we're looking at, I don't know, I can't say it exactly, but let's say I'm going to guess, I'm going to call that 54. So this is our 25th percentile, and I'm going to call it 54 because I can't quite tell exactly what that is. We're estimating anyways, these are approximate, so I'm estimating 54. Then we need 75th percentile. So 75th percentile is, half and half, about right there maybe. Let's draw all the way over. So our 75th percentile appears to be, I don't know, 78 maybe. There's our 75th. And like I said, it's about 78 is the actual value. So if we were to do Q3 minus Q1, we're going to be getting 78 minus 54. And that's going to be approximately 24. So that would be my approximation. It looks like their approximation is actually 20. I suppose you could have just known right away it wasn't 70 because the entire range of the entire dang problem is 70, actually, from 30 to 100. So definitely going to be letter D for our correct answer here. Letter D up there in the corner, D down there. We're done. We're moving on to the next page. Throw that paper away. We don't need it anymore. Here we go. Question number 4. The distribution of household incomes in a small town is strongly skewed to the right, so not normal distribution. The mean is 42,000 and the standard deviation is 24,000. Fornoff's family household income is 60,000. What is the z-score? So please, you are allowed to still use z-scores. It has nothing to do with if it's normal or not. It is not a normal distribution, and that's fine. We are just going to be calculating our z-score. So if we are not aware of that z-score formula, we're talking about z is equal to x minus the average over the standard deviation. You might see it as z is equal to x minus x bar divided by the standard deviation. And heck, if you even want the rules, the words for it is a z-score is always equal to, and it's going to be the person's value or score, so the actual value minus the average or the mean, depending on which word you want to use. They're very similar, divided by the standard deviation. So the standard deviation there is going to be our actual value. We're going to use one of these. So this problem looks like the score, the Fornoff family household is 60,000. So we're going to go ahead and say it is 60,000 minus, in the mean, it says in the question, the mean income 42,000, and then divided by standard deviation 24,000. And yet again, I recommend using that calculator to its fullest extent. And that's exactly what I'm going to do. So we're going to go ahead and use our alpha y equals enter to get that fraction going. 60,000 minus 42,000 divided by 24,000. There you go. 3/4. So if you're comfortable with it, you can just go ahead and write answer 3/4, 75 cents right away. Or again, alpha y equals, and then that number 4 for that fraction to decimal, convert to 0.75 for you. Letter C is our correct answer. Let's move on to question number 5. We've got a long one to read. I'm going to zoom out a little bit to actually read this whole thing. All right. The mean height of men in the United States is 69 inches. Standard deviation is 3. For U.S. women, the mean is 64, and the standard deviation is 2.7. The tallest woman in the Women's National Basketball Association is Brittany Griner, who is 80 inches tall, 6 foot 8 inches. The tallest current player in the men's NBA is Hasheem Thabeet, who is 87 inches tall. Which player is taller relative to the same sex in the U.S.? So what we're going to do is we're going to use the z-scores. And we're going to calculate the z-score separately. So we're using Griner and Thabeet. So let's do z. I'm going to use a capital G for Griner. And so we're going to use the woman's version of that. So it looks like her actual value is 80. And then we have to subtract the mean. So for U.S. women, mean is 64. And standard deviation is 2.7. Let's go ahead and set up the formula before we go to the calculator for the other one. So we'll use T for Thabeet, the Z for the Thabeet situation here. It looks like his score is 87, minus the mean is 69 inches. The average is, I didn't know that. Oh, it's for the men in the United States, not for for basketball players. I was very surprised. Okay, anyways, I'm done talking. I was like, there's no way it's only 5'9" is the average for basketball players, but I'm done talking. Okay, we're going to talk about the question. Where are we at? 3 inches here. Equal to, so that's our standard deviation. Now we just have to actually divide it up. So using our calculator, we're going to use again that alpha y equals enter button. Maybe I should just have it zoomed out this whole time. I don't know. I'm sure people can zoom in themselves if they needed to. All right, 80 minus 64 divided by 2.7. So it looks like Greiner's z-score is 5.9259. We'll just go 4 decimal places if available. And alpha y equal enter for Mr. Thabit here. Why am I hitting the alpha button again? 87 minus 69 divided by 3. And that's exactly 6. All right, cool. So which one is bigger? Looks like the beat is bigger, so that's what we're looking for. So the beat, because his z-score is greater. By the way, 6 standard deviations above the mean is absolutely insane. Definitely one of the tallest people on the planet in their respective categories for both people. Even above 4 would be kind of crazy, but 6 above is very much above the mean. All right, so number 6, distribution data set is normally distributed, blah, 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 blah. If you calculate the standardized score, big idea here, standardized score, anytime you have a standardized score, by definition, the mean is 0 and the standard deviation is 1. You're done. You can write the answer, my little spot up here. Letter C. So that's just a straight up rule. You'll see that in your calculator, by the way. You know, when you're doing the normal CDF or the inverse norm, you'll always have that mu is 0 and the standard deviation is 1 because those are the standard normal values. So they will always show up as that 0 and 1. All right. Next one for this density curve. Remember a definition of a density curve here. Biggest thing is the area underneath by definition is always equal to 1 or 100%. 1.00 is 100%. So what percentage of these observations lie between 0.2 and 3.8? Also, this exact one, if you didn't know, this is called a uniform distribution because it's completely flat. Don't know if that's going to matter to you later, but it's called the uniform distribution. And we're looking for what percent, or the area, in other words. This is, again, looking for area and maybe area times 100 for percent. What percent lies between 0.2 and 3.8. So 0.2 is going to be like right here. And then 3.8 would be about right there. So it's asking the area of this rectangle. Because the area of a rectangle is the length times the height, we are just looking for the area of this rectangle. You got length times the width, maybe, instead of length times height. The length of this thing is going to be the distance from here to here. So to find that distance, we're going to have 3.8 minus the 0.2. So you're just subtracting these two numbers, taking the distance between these two, 3.8 and the 0.2. Maybe I should have written that, 3.8 and the 0.2. And they're going to multiply it by the height, but the height or the width for every single one of these is going to be 0.2 as well, because it's like that height up there. That's pretty much it. So whatever that happens to be, when you plug it into the calculator, I mean, you can just plug it in as it appears, but I'm telling you right now, this is definitely going to be 0.72, but don't forget, you got to multiply by 100. We'll get that 72%. We're all done. Letter E again, CCEE for that page. Boom, boom, boom. We're done with that page. Let's move on to question number 8. Which of these variables is least likely to have a normal distribution? So in general, this is not the easiest question, and it won't be an AP question, but it's good to think about. The correct answer is actually right off the bat, letter A, income. Income is generally not normally distributed. In fact, income is almost always top heavy, meaning that there are income distributions are going to end up looking like this, kind of like that, where it is clumped up in one spot and there are a few people over here making millions and millions of dollars. And that's actually going to be true even at a local high school. Maybe not millions of dollars, but there are a few people, such as the principal, the vice principal, who make a lot more money than everyone else in the building, who's all going to be clumped up over here. And there might be some people over here on the left who make a little bit less money, such as the aides, or maybe some part-time workers, or people of this nature who are not always working at the school. but where most teachers will be kind of in this situation. So that would be what this is going to be. It's not going to be a normal distribution. However, it is important to notice all four of these are completely reasonably normally distributed. Lengths of hatch pythons in general, heights, lengths, weights of naturally occurring things are normally distributed. Human heights are normally distributed. The weights of dogs are normally distributed. How much food cats eat is normally distributed. There's so much stuff that's normally distributed. It's kind of crazy. Yeah, even the amount of soda in the 60 cups that are filled in an automatic machine, that's going to be normally distributed. There are a lot of things that cause normal distribution, and we'll actually explore what types of things will result in normal distributions later in the year. For now, we just kind of accept that there are a lot of things in life that are normally distributed, but not everything. Definitely not everything, and certainly not incomes. Incomes are almost never normally distributed. All right. So the heights of American men aged 18 to 24 are approximately distributed. I just said that with a mean of 68, a standard deviation of 2.5. What percentage of men are over 70.5 inches tall? There are two approaches to this question. So the question that they kind of expect you to approach it as is going to be a complete non-calculator approach. So let's go through the complete non-calculator approach. The complete non-calculator approach uses the empirical rule. The empirical rule states that for any normally distributed situation, if you are between plus or minus 1 standard deviation, you will get 68% of the population. If you're at plus or minus 2 standard deviation, you'll be at 95% of the population. And if you're at plus or minus 3 standard deviation, you'll get at 99.7% of the population. So we're talking about the area under the curve, just like the other density curve. And for this particular question, the mean, that mu value, the middle value is going to be 68, and our standard deviation is 2.5. So if I were to just add those two together, we would be able to, because that middle value is our 68. And if I were to simply add that distance of 2.5 right here, I'd get to 70.5, and it wants to know what percentage is over. So we're looking for this area over there. Because we're looking for that area, and because the normal distribution is completely symmetrical, within plus or minus 1 is 68%, which also means, though, that on the outside of those two is going to be 32%. So on the outside of it's going to be 32%, and 32% divided by 2 is going to give you that 16, because there's going to be 16 on this side, and then there's also going to be 16 over here that are actually, I don't know why I drew it right there, 16 over here as well. So there's 16 on both sides, and 16% is going to be our correct answer. However, this is a question where the normal CDF button on the calculator will do all of the work for you, and I kind of actually recommend using it. So let's check this out. Anytime you're given all of this information, you're given the mean, the standard deviation, and you're asking for over, you can simply use our normal CDF button on our calculator to enter this in. So we're looking for over 70.5. We will hit second, and then vars, and then normal CDF number 2. Second vars, we get over 70.5, so 70.5, and then the upper value here is going to be 99999 because it's going to be as large of a number as you can imagine. It is actually still appropriate to simply enter the upper number as the tallest person there is, because it's approximately normal distributed, and you'll get almost exactly the same answer, and you probably will get the same answer even till 4 decimal places. And now we're going to enter in our mu. Our mu is 68. Our standard deviation is 2.5. And boom, bada boom, we end up with 0.15. We are looking for a percentage, so we'll multiply that by 100. And if you multiply by 100, you get 15.86. And that's really the perfect answer, but they're doing an approximate answer of 16 because they were assuming that you would use this empirical rule. All right, number 10, let's check it out. The distribution of heights of students in a large class is roughly normal. That'll be true as long as the class is big enough, by the way. As long as it's at least 30 students, that will be a true statement for quite a few classes. Not always. Not always. I shouldn't have said that. That's probably not a good way of looking at it. At least 30 for the sampling distribution to be approximately normal, but that's another story. We'll worry about that later. Moreover, the average height is 68 inches, and approximately 95% are between 62 and 74. So what they're trying to say with this information and the problem is giving you is it's giving you this information that in between here and here, this is 95%. 95% of our population is in between 62 and 74, and the middle value here is going to be 68 for our mean. In addition, we can use this plus or minus 2 standard deviations rule that we said before to know that this here and here, this is our plus 2 standard deviation, this is our minus 2 standard deviation. So in other words, the entire distance from here to here, which is 74 minus 68 equal to 6, that is 2 standard deviations. Half of that, that is to say 6 divided by 2 to give you 1 standard deviation, is 3. That is one way to approach this question. Another way to approach this question is to use the calculator. There are a few different methods of using the calculator for this. The method that I would kind of recommend is to use the z-score formula. So the z-score formula is going to tell us that we want to know what the standard deviation is for this whole population. And we could figure out what the z-score is for a given score of, say, 74, and then subtract the mean of 68 through using that same z-score formula, and then you get to divide by a standard deviation that we don't know. However, we can figure out what that z-score is. You can find this, use the inverse normal button. So the inverse normal button to do that, actually on these color calculators, the calculators that have the color on them, or just an updated version of the 84 will have this. If you don't have this update, there is a way to update your calculator, and I recommend Googling it, or ask your teacher to update it. Maybe your teacher knows how to do it. Regardless, second vars, and we're going to go to inverse norm, and we are going to do our area is going to be 0.95, and actually mine's not even updated. Look how great this is. I'm trying to show these cool things with these like left, center, middle, and my own calculator's not updated. Kind of embarrassing. You can't even use the 0.95 version. You're going to have to enter in 0.025. Where did I get 0.025 from? So what I did is I am actually using the negative of the other side. If there is 95% here, that means that there's going to be 5% on the outside divided by 2 is 2.5%. That means here is 2.5 and here is also 2.5. So if those two things are both 2.5%, if I enter in this area in the calculator is 0.025, that's 2.5%, and I simply hit enter, it will tell me that this z-score right here is negative 1.95 to get right there. And because it's perfectly symmetrical, that means that this z-score that I'm looking for is positive 1.95. 74 minus 68, by the way, is 6 divided by our standard deviation. Let's flip-flop those two to solve. The standard deviation is 6 divided by 1.95, and if you notice, it's super similar to that 6 divided by 2 that we did earlier. 6 divided by the 1.95, and we get 3.07, or approximately 3. That was the harder way of doing it, and if your calculator's updated, I gotta update my own calculator here. It'll have the left, right, center, and I could have used the 95% center button instead to get that positive 1.95. All right, question number 11. Suppose that 16-ounce bags of chocolate chip cookies are produced with weights that follow a normal distribution with mean 16.1, standard deviation 0.1. Approximate what percent of the bags would be likely to be underweight? So yet again, this is a question where we could simply use our empirical rule. And the empirical rule, just drawing up this picture here, so we have a mean of 16.1, and we want to know what is less than 16. So we're looking for this area over here. If you notice, this question is actually identical to question 9, just on the other side, because this 2.5 is our 1 standard deviation above, and we get that 16%. This is going to be exactly the same thing because this is negative 1 standard deviations away on the other side. So this will also be roughly 16%. Yet again, we can use our normal CDF button on our calculator to solve where this is. Let's go ahead and find that out. We're going to go ahead and hit second vars normal CDF, and we are trying to figure out less than 16 ounces. So we can actually leave the lower at this. This is negative 1 times 10 to the 99th power, so that's going to be like negative a bunch. And because it's negative a bunch, we can just leave it like that. Or we can just do negative 99999 because that's what I do in class. However, it was also reasonable to leave it as 0 because this is a situation where you have bags of chocolate chip weights. You can't have a negative weight of chocolate chips. Either way, the upper is going to be 16 because that's what we're looking for. We're looking for 16 or less. Our standard deviation, we were told, is 16. Our average, our mu, is 16, and our standard deviation is 0.1. And sure enough, we're going to get Whoops, I didn't type in 16.1. Yikes, yikes, yikes. That's not what I wanted. Normal CDF. Mu is 16.1, not 16. There we go. Now it's right. Well, if it is, if I actually... Yikes, Mr. Richards. Dude. Man, oh man, I am being cut from the team right now. There he goes. There's our 16%. Maybe multiply by 100 to see the 16%. All right, I'm moving on with my life. Here we go. Area under the normal curve corresponding to z greater than this. By the way, this is corresponding to the probability of z being greater than negative 1.22. That is the most common way of writing it, but it is still an area, still drawing the picture here, same exact idea. So this is basically saying if I have this normal distribution, we are expecting this over here. We have negative 1.22. You are able to do this problem using a table of values, but I don't recommend it. The normal CDF button on our calculator will take care of this for us. And I drew the picture wrong. It's greater than. This is a greater than symbol. Yikes. Clearly I should have taken a break a while ago, but I'm going to power through. I'm almost done. All right, so we are looking for this area instead. We're looking for greater than. So we're expecting a value much bigger than 50%. In fact, right away, just looking at the drawing, we can immediately cross off these three because they're definitely not bigger than 50%. It's got to be between one of these. And those are so close to each other that we really do need to use that calculator. Again, you can use that table of values if you really, really wanted to. I'm not going to do that. Our lower is negative 1.22. Our upper is going to be 999, and it's a standard normal distribution. So our mu is 0. Our standard deviation is 1. We hit enter. We do it up. It's 0.887. So rounds up, I suppose, to that letter E. I didn't even fill in these answers over here. What do we got? We got B, B. Boom. All right. Greater than 1.25. This question is almost identical to this. I'm not even going to show any work outside of what I wanted to show in terms of that 1. This is 0 in the middle, so 1.25 will be over here. This should have been obvious. There's 202, 1.25, and we're going greater than, so over here. So we expect a really, really small number. So unlike the previous question where we crossed off the ones that were above 50, we're going to cross off these ones because it's definitely not true. In addition, 16, we kind of know that 16% from these previous questions is exactly 1 standard deviation. So I think it's also reasonable to cross that one off and know that it's between these two. Let's do it. We got second bar is normal CDF, and we are doing a lower of 1.25. Upper is already there. Standard deviation, standard normal, we're already there. 0.1056. Boom, bada boom. Let's move on to the next page here. I didn't even throw it that time. I just set it down nicely. All right, so the scores are normally distributed with a mean of 62, standard deviation 11. Bottom 5% of the students will fail the course. So what is the lowest mark student can have and still be awarded a passing grade? This is a question where they have given you the percentage instead of asking you for the percent. So if you are given the percent, given the percent or percentile, instead we're going to use the inverse norm button on the calculator. They're basically saying that we know on this distribution here that the middle value is 62. We know that from here to here, we know that distance is 11. You know, from here to here is 11, and therefore, you know, it's like 73, and this is like 51. And they want to know the bottom 5%. They want to know what value would make this area 0.05. What would make that 0.05? What is this number right there that would cause that to happen? This works with the inverse normal button on the calculator. So using that inverse normal button on our calculator, we're going to go inverse norm there, and the area that we are looking for again is 0.05. Luckily for this, they give us the standard deviation and the means. We can type those in. If they didn't give them to you, you would have had to use standard normal and done some extra work. We don't have to do that right now. And they get this value of 43.9. So that's 43.9. So if you get 43.9 or lower, you will fail. So you have to get higher than a 43.9. So 44 is what we're looking for. Boom. Number 15, 40-pound bags of birdseed do not have exactly 40 pounds of seed. No, they are approximately normally distributed. They're done from a machine. What is the weight of seeds approximately normally distributed with a mean of 40, standard deviation 0.25? And they're given the percent. You're given a percent, you're given a percentile, so exactly the same setup as this previous question. I'm not going to draw anything up. We're just doing our inverse normal yet again. So we're going inverse norm, and we are going 0.9 this time, 0.90 if you really want to, and it looks like 40 and 0.25. So 40 and 0.25. And it looks to be that 40.32 is our 90th percentile, so 40.3. Boom, boom, boom. All done talking there. Number 16, the mean age is approximately normally distributed. And we actually researched this during class with mine. This is not a true statement, so I don't know why they said that. But Barack Obama was 47 when he's inaugurated, which is the 11th percentile. So yet again, they gave you the percentile. However, like I said in a previous question here, they didn't give us all the information. They want to know what the standard deviation is. So what we're going to do is this two-step process. We're still going to be using our z-score formula, just like in I had set up on like the non-empirical formula way. Our z-score formula here is going to be 47 minus the average of 54.6 divided by our standard deviation. So that's the only information they give you, but you can use the inverse norm feature to find this button on the calculator. So again, this is going to be found from the inverse norm on the calculator. So, but this time, when you're looking for z, you have to use the standard normal values. You can't plug in the mean and standard deviation because they don't give it to you. So we have to use our standard normal values. So here we're going to be using our calculator yet again, second vars, inverse norm, and we are looking for 11th percent. So 0.11 and a mu of 0, standard deviation of 1, negative 1.2265, 4 decimal places, always on the AP test, negative 1.2265 equal to 47 minus 54.6 divided by our standard deviation. I should have done that subtraction, but regardless, when you're doing this stuff, you're going to switch the positions of the standard deviation and the z-score there to get to our final answer. So whatever this happens to be dividing into. So let's do that. Alpha y equals enter 47 minus 54.6 divided by negative 1.2265. Turns out to be 6.19. So that's actually the perfect answer. Their answer is kind of rounded incorrectly, but you know what? Whatever. Life goes on. C. That one was A. Really bad A. All right, let's do our free response question now. So here we go. This free response question, I've already read it before, so I guess you can read it again though. The average starting salary for company X is $50,000 with a standard deviation of 2,000. The average starting salary for company Y is 48,000 with a standard deviation of 3,000. Susan works for company X. Livy works for company Y. Both Susan and Livy are given a starting salary of 52,400. So this is very, very similar right away to that basketball question from earlier with the comparing the heights. And that's exactly what we have to do. We're going to have to do letter A. For letter A here, we are going to calculate two different z-scores. So we're going to have to do a z-score for Miss Susie at company X and a z-score for Miss Livy at company Y. So maybe I'll just do that. Maybe ZSX and ZLY so I can easily remember. And we have to do her actual, they both get 52,400. So 52,400 for both of them to begin. And then you have to subtract to the average. Company X is 50,000. Company Y is 48,000. Divide, and you're dividing by the standard deviation. The standard deviation for this company X is 2,000. Standard deviation for company Y is 3,000. And you just got to plug those bad boys into the calculator. I'm not going to show myself doing it because I did this already earlier today. But when you do this, you get exactly 1.2 for this one. And maybe I do have to do this one because I don't think I remember this one off the top of my head. Yeah, I don't remember it off the top of my head. Remember that one was exactly 1.2. Maybe I should double check. You know what? I got a question wrong yesterday, so I need to double check it. Have faith. Well, yeah, it's 1.2. Okay, I don't know why I did that. I know that 6 over 5 is 1.2. That's silly. All right, anyways, 52,400 and minus 48,000 divided by 3,000 alpha equal 1.4667. always 4 decimal places, and therefore we can write a sentence. We can say that Libby makes a relatively higher starting salary because her z-score is higher. Her salary's z-score is higher. Salary's z-score is higher. Libby makes a relatively higher starting salary because her salary z-score is higher. I apologize for my handwriting. Letter B. All right, assume the distribution for the starting salary at company X is approximately normally distributed. What is the proportion of starting salaries at company X that are less than the average starting salary at company Y? So in this situation, we are trying to figure out what proportion are higher than the average starting at the other one. So they both actually started here, but they have different average starting, right? So the average starting here is 50 and the average starting is 48. So we need to figure out for basically a probability. We're showing a z-score calculation. So I'm going to go ahead and write down like all the work for it, what we type into the calculator, what we're actually calculating, but what we're really doing is going to be doing this. So we're going to be doing the probability of the z, and in this case, the proportion are less. So what is the proportion of starting salary companies X that are less than the average starting at company Y? I need to take a drink of water really quick. Okay, I'm back. So we're looking at the probability of for starting company X normally distributed and probability of that company X being less than the starting at company Y. So the probability of company Y here, company Y is 48,000. So we're looking for that are less than. So probability of Z being less than 48,000. And then you're subtracting the average, and the actual average that you're subtracting here is 50,000, because we're doing all these for company X, right? So this is for company X. We're using the company X values of 50,000 and 2,000, and that's what we're calculating, right? So you could just calculate this using the standard normal table of values, could using the standard normal calculation in the calculator, but the easiest way is actually going to be using your normal CDF button. So I'm just going to write down exactly what I'm going to be typing in here so you can like see it for yourself when you're writing this down, maybe on like a test or a quiz. So you have normal CDF, and then you're going to be doing a lower, an upper, you'll have a mu and a standard deviation. So our standard deviation here is 2,000. Our mu is 50,000. And then, by the way, these numbers are like perfectly set up in a way. The reason why they're perfectly set up, you'll notice is exactly -1 when you do all this workout. So we're expecting to get to 15.85%, that same about 16% that we did earlier. Either way, the lower value is going to be -99999, and actually it's really appropriate to use 0 in this problem if you wanted to, because it's money. Again, you can't have a negative value. And then the upper in this problem is the actual score of 48,000. But what's important, I think, for understanding is that you understand that this probability calculation is the same as using this normal CDF button. Yeah, I think that's what matters in terms of like overall understanding for the AP test. All right, we're gonna go ahead and do this guy here. Second vars, normal CDF. Literally just typing in what I have here. 48,000, 50,000, 2,000, and there is our 15% that I was mentioning before, but it doesn't say percent or proportion. It does say proportion, so you do not need to write it in percent form. So we're going to go 0.1587. Looks like that's what the rounding goes to. You'd probably be acceptable to write 0.16, especially if you wrote something about the empirical rule in the actual AP test. All right. Letter C, estimate the third quartile. So estimating the third quartile, remembering from earlier, I'm going to go ahead and switch color to red for this one because I don't want to get a new sheet of paper, even though I have paper right below it. I don't really want to. Estimate the third quartile for company X. Remember that this third quartile here is Q3, and that is always equal to the 75th percentile. So, and anytime you're looking for that 75th percentile, you want to use that inverse norm button on the calculator. Yeah, that's what we're going to be doing. We're going to use the inverse norm on the calculator. And for that inverse norm, we're going to do 0.75. And then we're going to use the exact same mu and standard deviation. And that's what we're going to do. However, I do want to mention something right afterwards for this one. If you want to do it like a pure AP style, what you could do. So by the way, if you don't know where that inverse norm is again, second vars inverse norm and area is 0.75, our average 50,000 and mu 2,000 here, and it appears to be 51,348.98 is dollars. I didn't do 4 decimal places because it's money. You should not round more for money. But I did want to mention, ooh, why did the color change so drastically? I wonder what happened. Oh, that's weird. Like the changed yellow because the polar curve showing up on my calculator. Sorry. That's a pre-calculus topic or maybe a calc 2 topic if you're doing integrals, doesn't matter. So yeah, it does turn yellow when I put the calculator up. That's so strange. There's got to be a color correction automatic on here that I don't want. I'll have to fix that later. Either way, the point that I'm trying to make out is that for the inverse normal, what I could have done on my inverse norm is I could have left this as 0 and 1, and that would give me a z-score of the third percentile. So like the z-score for the third percentile, or the third quartile, sorry, 75th percentile. If I was like to do a z-score calculation, I could do 0.6745. And then set that equal to what we're looking for. So what it wants to know what proportion of starting salaries. That's the actual the z-score for the 6th, 7th percentile. So now we're trying to figure out what is the starting salary. So what is the score? So we have x minus, and the actual score would be the 50,000 here on the bottom, and then the 2,000. So I can multiply both sides by 2,000, so times 2,000, and I would get 1348.9795 is equal to x minus the 50,000. Add 50,000 to both sides, and if I did, I would get an identical answer to what I got up here, right? So I get the same answer either way. The point that I'm trying to say is the inverse norm is just doing this calculation. That's all it's actually doing. Other than that, have a great rest of your day, and peace out, guys.